My name is Carl. I'm from Microsoft. I'm from Dublin in Ireland, and I work on the HPC team in Microsoft, and I cover countries in Europe. I cover 12 countries in Europe, and I work with customers, I work with partners, I work with scientists like yourself, with researchers, and I help them to use HPC in the cloud, in the Microsoft cloud. What I have for you today is actually a cut down version of a workshop that we will be doing around Europe in the next 2 months. So this is what it is on the slide, and really it's basically a little introduction to what HPC in the cloud is and what it is in Azure. And then we do a little bit of workshopping around some of the fundamentals, so how to make some virtual machines, how to connect to them, how to scale them, grow them, shrink them, and using then different services we have, like Azure Batch AI, something a bit cooler, and then we have more specifics. So all of you will have your own particular interests, your own domains, and you will want to do different things. So we have a lab online where you can choose different labs to do. So there's a link here on GitHub. Some of the content is not complete. We can share these slides afterwards, but you can also dig into whatever you like. So this is a full day workshop, but we only have 2 hours. So what I will try to do is maybe give you an overview of everything. So my goal is to try and give you a little picture from my world, my view into Azure, into the cloud, the focus on HPC. But please, of course, if you want to know anything, you can ask any questions. We can talk about anything you like. So maybe the first question is, has anybody used Azure before? Okay, a few. That's great. That's great. Has anybody used other cloud services before? Amazon, Google, anything? Okay. And has anybody done any HPC on any of these clouds? Any computing? A little bit. Okay, great. So if anyone has access to Azure at the moment, so anyone can sign up for free. I don't have anything access to give you now, so the workshop today will be basically, we'll talk through a few things. Maybe we can have a discussion. I can show you some things on the screen. And if you have access to Azure, you can follow along. If you don't have access to Azure, everything is available online. You can complete different things that you choose afterwards. And of course, please, you can contact me after the workshop. I'm happy to help you with anything that any questions you might have, any things that you want to learn. So really, this is just to give you a picture of maybe what's possible, a few things to do. If you want to try a few things, great. And that really, the goal for me is to give you a bit of a picture about what is possible, what you could do. Okay, so let's see. Okay, great. So let's move. Let's get started. Just a little bit about me then. Like I said, I'm from Dublin in Ireland. I am only with Microsoft 1 year, but I've been working in IT and in HPC for about 15 years. So I worked with Bloomberg, a large financial institution, for a year. I worked with Tullow Oil, an oil company in the UK, Ireland, Africa, Norway for about 5 years, and I ran their HPC, I ran their supercomputing. I was a Linux systems administrator, so my career has all been as a Linux guy. So actually I was a postgraduate student. I did my research in computing, in bioinformatics. I used Linux all of the time, and then I left academia. I went to go get a job, and I was a Red Hat system administrator, SUSE. I ran lots of HPC also for customers in Ireland and the UK. And now, basically, instead of building physical machines and putting things together and helping people, we have the power to do that so much more easily. So with a few clicks, a few commands, we can create something, a huge power that we might not have been able to create before, that might have taken months, years to actually make and produce. And all of this is changing all of the time. So everything I show you, there'll always be something new that will come out all of the time. So really you will have access to the latest hardware, the GPUs, the CPUs, the memory, anything that you may need to do your science, to do your simulations. All of this is changing all of the time at such a pace, such a scale across the world. So this is really a great possibility that we have with the cloud. I never thought I would work for Microsoft. I never thought as a Linux person that I would work for Microsoft. But you know, the world is very different. The world changes all of the time, and there's a lot of things that are changing in Microsoft, and I've learned a lot in the last year and a half that I've been there. Okay, right, let's go on. So this was a little bit more of the agenda. Like I said, I will give you a little bit of an introduction now. We'll talk a little bit, maybe I'll show you a video or two. We'll talk a little bit maybe through some demos or something. And then there is a little bit of kind of workshop activity in the last half. So if you have access to Azure and you want to try, that's great. You can sign up for a free account right away. Maybe it will ask you for a credit card, but it won't charge you. So you get, I think, 200 euros free for a whole year. You can try whatever you want. So if you want to do that, please feel free. If you don't, that's fine. And also we can maybe provide access afterwards, maybe get some tokens or something that you can use. So maybe I was not so organized for today to have that ready, but at least it's the goal is to try and to give you a better picture. Before I start, are there any questions from anyone about what I've said? Is there anything in particular people would like to know?
I don't know what the focus will be or how you will talk about everything, lots of things, but I'm particularly interested in security.
Yeah.
Cloud security as Microsoft sees it.
Sure, absolutely. So while I probably don't have a lot of security focus in this because it's very HPC focused, and I can definitely talk to that, and we can go a little bit more into that. Because actually that's one of the things that is most important for us. It's actually trust. So a lot of people maybe were scared of the cloud for the last few years. They think, well, you know, this is not my computer, it's somebody else's computer. How can I trust? How can I trust Microsoft if I put my data, if I put my computing there? And so we'll go a little bit into that, but basically there's no way that we would be able to do what we have done so far without trust of you, trust of customers, trust of people using the platform. And the reality is also I ran an operations team, I ran a computing center for a number of years, and the security that I saw when I went to the Azure data centers was far, far greater than anything that I would have been able to build myself or build on site. I have a little video that might give you an idea of that, so you can see a little picture of the data centers. And the reality is that a lot of our data centers are more secure, more certified, more trusted than what a lot of people currently build. But hopefully we can get into a little bit of the details of that. Anything else from anybody before we get going? Okay. Okay, so I have a few structure that we might talk through here. I want to say, why would people consider doing Cloud HPC at all? Then why would you do it with Microsoft Azure? What specifically about that could you use? And then let's talk a little bit more in detail about the solutions, partners, customers, what other people have done, and then we can get into some techie stuff as well. So one of the things we say, we also, this is probably like a marketing term, but people have heard of big data. You probably hear a lot of terms about big data. What does it actually mean? All of the data and the things that we have to deal with. Well, one of the reasons that cloud is here also is from a HPC perspective to help more people know that they have this power available to them. So that not only yourselves doing your science can do your research here, but that anybody can do it. So instead of having a whole supercomputer center, one person can have a huge amount of power available to them with the push of a button, a few commands. And so this is actually bringing HPC to more people. So this is what I like about the whole thing. So it just makes it easier to use. You can template things, you can write it as code, you can save what you're doing. So no more do you need to make complicated clusters together. Maybe the configuration won't be correct. You know, there's a lot as well that people are sharing online. This is really making this available to everyone. And people who develop software are building their software on top of this platform as well. So really, this is also making their software available to people. So this is putting it in the hands of more people. when we talk to people inside Microsoft, they don't know what this is, but we want them to know what HPC means to so many people. So these are samples from customers that we've working with closely already. One of our biggest customers is in financial services. So every day, basically large calculations are made for risk, financial risk in the markets. What happens if I buy these stocks at this time, what this scenario would look like. So banks run hundreds of thousands of cores on Azure to run these risk simulations to find a better picture of what will happen in the future. For insurance payments, so when your car insurance or your house insurance premium comes through, insurance companies are running these calculations, highly parallel calculations. Not a lot of them are sort of very tightly coupled or with a lot of data interaction. So this has sort of been the first scenario, right? So people were worried about performance in the cloud. Maybe we can't actually get the performance that we want. So actually, the best ones were ones maybe that did not so lot data I/O. They were just really in the CPU. They were very easily parallelizable. But really, with a lot more power that's come in, we have Infiniband networks, we have GPUs, we have very tightly coupled networks and storage solutions, so people can do real HPC now. So people think that they were not able to do real HPC. Any clusters that you typically get, they're possible to do now. And people are doing these at like 100,000 cores, 200,000 cores. This is kind of the scale as well that some customers are doing these things at. So of course, they also use it in video rendering, oil and gas, where I used to work, where they try to find a picture of what the subsurface looks like, where we send our sound waves to the ground, we collect them, and we try and do a calculation to find out what underneath the ground might look like. So for all of geoscience, not just in oil and gas. And climate modeling, of course, as well, finite element difference, and of course we're doing a lot of work then in genomics, life sciences, pharmaceuticals. So these are the big industries, customers that we have. But really we want to make the world a better place. I hope all of you here are also interested in HPC for that reason, because whatever about big data, if we can make big compute something that people know about, and we can put computing into the power of more people's hands to do more simulations, to think better about what could happen in the future, then really we're giving more people this power. So that's one of the things that is our goal and that we're trying also to do. So like I said, it's about doing even more as well. So major car companies are also using us as they would use a lot of HPC on-premise instead of crashing a car physically, and how much money this costs to do this every single time you crash a car versus running a simulation. So I think many of you probably already know the power of this idea, but if you can run a simulation, you can tweak a variable, you can change how sort of a stream is working, how a door might work. Really, you can do a lot of these scenarios before you then do this. So maybe you do many of this, and then you maybe do one or two of this to get a better idea and to prove in the real world what your simulation might be. So this then is with the cloud, what would you do if you had extra power? So a lot of us think also about our simulations in what we can do. What is my workstation? What is my cluster? How many cores do I have? And I will try and fit my simulation in that. But what if we were to change our thinking? So what if we were to say, well, what would be possible if? So if I had more cores, if I had more memory, if I had unlimited power or a relative unlimited power, what would I do? Would it make me think differently about the simulations that I'm doing? Would I envisage a different scenario? Would I try to do something? So this is also what we want to do. We want to try to help people think outside of the box, because we always think in our box. We think in our workstation, our laptop, our cluster. So maybe if you had more cores available, so maybe if you had 100,000 cores, but you only ran them for 1 hour. So maybe that would be something that you could do an experiment on or a simulation with. And you could think differently about what you're trying to understand or trying to learn. So this is what we also say. So if you had a lot more scale, you could also service more people. Maybe you could do more projects. Maybe you could do things faster. So we know not all things will scale. Not all models are going to scale just because we throw more power at it. Depends on the model, the way you've written the code. But maybe some of them will. So some of the scenarios, if they're linear, we can just throw more cores and maybe we can get something done faster. So for large companies, especially financial companies who maybe have a lot of money and there's new financial regulations. All of the banks, and we know this in Europe, all of the banks have to do better to look after our money, right? And to understand what's going to happen. So they have regulations to meet. And as a result of those regulations, they have to do scenarios. So if they have to get something quickly, so instead of, if they really need something for a deadline to meet a regulation today, instead of next week, and they could do 10 times faster, or 10 times more what they could do, and they could get it done in 1 hour, okay, maybe it will cost more money, but it will be very important to them to meet their deadlines. And that's also what some of the customers are currently using Cloud HPC for. So this is also the thing. So if you can think a little bit differently about what your simulation, your parameters, and what maybe you might do a little bit differently. This is some of an idea of different ways that customers use it. So not everyone will have the same type of profile, and in your, in your fields as well, you may not also. So maybe you don't, we're used to maybe something like, say at Mare Nostrum, which is a center, it's running 24/7. It has a queue of jobs that are running on the cluster the whole time. The cluster is maybe 90–95% full if they can get it to that. But not everyone will work like that. And also maybe you are just one person amongst a sea, amongst a group, to run your simulations. So when you're running your simulations, you maybe don't do them all of the time. Maybe you do them once a week, once a month, once every so often. You want big, you want small. So these are the different profiles that people might use. And if you know this, then you can plan better. So if you know what your simulation will be, and you maybe know what you will need, you can also plan and do things cheaply. So for example, if you know I will always use 10 machines, these cores, then maybe you can guarantee that for 1 year, for 3 years, and you can really get a huge discount. So in terms of cost, instead of buying a machine or buying a group of machines and looking after them, really you can get huge discounts if you know the type of computing that you will do, how much you will do, how often you will do, and if you can plan, then really there's a lot of savings to be made versus actually buying a machine. So if you go right now, there's an Azure public calculator. It's the same for all of the other clouds. And you can go, I'll have this machine and how many hours. And if you do a calculation right now for 1 year, 24/7 versus buying a machine, it just is too expensive. The cloud looks too expensive. So if that's the model that you want to run, things are maybe not also the way to go. So really the way people are working with this is when they're measuring closely against the computing they have to do, the simulation they have to do. So really when you know that, and as researchers actually you know this a lot better than the IT departments. The IT departments see these machines, these supercomputers as resources they have to keep and use and work all of the time. But if you as researchers are running code, running a simulation, you only think in these terms, you can start to think a bit clearer about what, when, why you need to do it. And then why do you need to have a particular resource all of the time available to you? So this is one of the PowerPoints of the cloud. This is a sample customer usage we have, and you can see how they scale up actually to 1,600 VMs, maybe on a sort of spiky sort of basis. So maybe they have kind of a common profile every week, the weekend, maybe nothing is happening. Every week there's something, and then maybe they do some spikes. Maybe they have a simulation to get done. Maybe you're writing a paper. You need to run the simulations as quickly as possible, and maybe the queue on the cluster you're running at doesn't have this. Okay, so this is kind of the power. So one of the things about us as well is that it doesn't have to be done completely in the cloud, right? We'll talk about some of the scenarios, but you can burst. So with systems that you might have on premise, which are workstations, maybe you do this most of the time, and then when you need the power, you can burst. So integrations are possible with software. So if you're running Slurm or Torque or PBS or SGE or any of these schedulers, you can integrate that with the cloud. You can submit your jobs, and then when they need to go larger, then maybe they will submit out to the cloud, run the calculation and come back. So there are many integrations also we have to be able to do this, what we call hybrid. So when you hear the word hybrid, it means partially on your site, on premise, and then partially in the cloud. So you almost just have one view as a user of the whole system, and then maybe when you need it, it will go out. You can be careful, you can specify rules, but this is what we talk about hybrid HPC. One of the important things is the results. So when you run your calculation, you get the result afterwards. You can have remote workstations in the cloud. So actually, if you create the data and the result up there, maybe you leave it there. You use and look at a workstation on the cloud and you see your 3D model, for example. You can maybe interact with it a bit, and there's many different ways to do that. Performance as well works, and maybe actually you could do everything in there, but the hybrid is also possible. One of the best things about this is it allows collaboration also. So say maybe you're working now here with people locally, but if you're working with researchers, actually after this workshop, I know you're from different places, you'll have made connections, maybe you want to work on a paper together. Well, one of the best ways to do that is in a central location. So if you're working together in the cloud, you do your computing, you do your results, no matter where you're located in the world, we have those locations available, and it makes it a lot easier to work together. So this is also a next generation HPC thinking. So this is maybe, I don't know if it's so applicable for everyone in the room, but we talk to a lot of people in IT departments who look after these systems, HPC systems, these clusters. And a phrase a colleague uses is he calls them cluster huggers. They want to hug their cluster. They love them. They love the machines. They name them. They look after them, and they think that we will come to take their jobs away and take their machines away. And it's not fair, it's not true. We don't want to do that. Of course, if they like their machines, they can keep them. They don't have to change them, right? But this is giving people an extra capability, an extra power, and a different way to think. So change is always hard for anybody. But as we have to work through and you can show the power and the potential, then it also helps. And really, all of the skills that people have in these departments, they know the software, they know the systems, they know how to put things together. All of those skills are transferable. So even if you know how to use Linux, and you know how to install your applications, and you know how machines will work together and networks and everything, that knowledge is still applicable in the cloud, and people still need to support researchers, scientists to do their work. So we have to also help. Microsoft traditionally has a lot of relationships with IT departments. They're used to going in and selling Windows, selling Office, but the relationships exist, and it's also our responsibility to help IT departments transform. So to think differently about what they're doing, and to bring them along with us on the journey that we have gone in. Because Microsoft has bet full in on cloud, right? If cloud doesn't work for Microsoft, then Microsoft is bust. Okay, so Satya Nadella, our new CEO, 3 years maybe, has been in, and this was one of the big bets that he made. And basically, if this doesn't work out, then that's the end kind of the company. But really, Microsoft are a software company. Of course, we have many other products and everything like that, but this is one of the things that we are using to transform ourselves as a company, our customers, our partners, everyone that we work with. If you talk to Microsoft people, they will use the phrase digital transformation quite a lot, because this is really what's allowing people to transform their business, do things differently. In HPC, 4 things to maybe think differently about with the public cloud. We bought a company last year called Supercomputing, and we have this tool called Cycle Cloud. So this makes it very easy to make clusters, systems in the cloud. So you can see here, there's a nice little panel. Maybe I want a Redis cluster, or a TensorFlow, or a Hadoop cluster, or MATLAB. And you can, with a click of a button, get access to this. When you submit a job, maybe it wants 100 nodes, then it will spin them up, do your job, and shut down. So the thinking of this is that you, instead of having one cluster for 20 people, you have 20 clusters. Every person gets their own cluster. They can run their own jobs, their own simulations, their own applications. So this is a different way of thinking for people who look after these systems. So this is what the Cycle Cloud tool enables us to do. The other thing is that I talk specifically about HPC, but there are so many other services in Azure which we will touch on. So there's over 100+ services. So there's data lake and AI and databases, and there's networks and storage and everything, right? So there's so many services that people are building. Of course, we have our core, compute, storage, networking, but people are building software on top. So instead of having you building AI into your application, maybe you can use the service, use the cognitive service API, and then you can do translation. So say, translate this piece of text from English to Spanish, this piece of text from Spanish to Italian, and you can just ask for that and get the answer back. You don't have to worry about it. So people are building those services in the cloud, and maybe you can also combine them with your applications. The other way is to think that it's all code. So a lot of people are used to plugging machines in, and that's very important to learn how machines work. But the reality is now we can describe all this as code. So you can describe an entire cluster, all of the compute nodes, the head node, and the storage and the networking, everything with a single piece of code. You can save that in your repository. You can spin it up lots of times. You can share it with people. You can change it. So really, this is a different way for people to think about infrastructure. And then finally, which is also, for a lot of people, interesting, of course, AI, machine learning, data analytics, all of these are the extra services that people are now building. Okay, we have our cloud, we have our compute, storage, networking. What's next? What else can we do? So this is where Microsoft is also investing a lot. We have these AI cognitive services I just mentioned, but there's also a lot happening in machine learning, in data analytics, and these services are being made available to everyone. So anybody can use them. And that's when you decide what's important for you. So when you're writing your code, what's important for your simulation? You don't have to worry about the stuff that's not core. So whatever is most important for you, maybe you focus on that. And the stuff that maybe you don't know so well, that translation or visualization API or some recognition of an object in a picture, maybe you leave that to something that's already been written. So you use these as building blocks. So from the HPC world, it's very traditional. It's a long time as an industry, and people are nervous in many ways about AI, machine learning, data analytics, things that have happened alongside the HPC industry that's been going a long time. So it's also to help see where these areas will interact. Okay, a little bit about why Azure in particular. Why would you use the Microsoft Cloud? So the 4 things that we mention or that we talk about that are different for us, the reasons why customers use it as a proof point is that we're productive, hybrid, intelligent, and trusted. So they're the 4 areas that we try to focus on and the reasons we see that customers choose to use Azure instead of using one of the other guys. Okay, so in particular in terms of productivity, this is one of my favorite slides because I like the change it shows. Microsoft a few years ago would never have been able to show you all of these logos together, right? So everything open source works on Azure. Basically about 50% of the virtual machines today running on Azure are Linux, some form of Linux. So this is really a change for Microsoft where when I joined a year ago, I actually met a person who had been in Microsoft 20 years, and one of his old jobs in Microsoft was to kill Linux. So 15 years ago, he had a job that they had to make Windows better, and one of his jobs was as a complete lead to kill Linux. So it was really interesting to meet him, and now he is working on the HPC team to help get these people on board. There's a lot of colleagues who have to change their mindset and ways of doing things, but the reality is whatever code you work with, whatever platform you're using, whatever framework you like, bring it and use it. The cloud is just available to you as a resource to use. Whatever you like, just use it. The Microsoft Azure is not just for Windows, right? And I know very little about Windows. I've only been learning in the last year. So this is the world that I like to play in. Of course, there's all of the other things that it brings as well. So everything that you know, Visual Studio. Visual Studio is open source now. So you can go and look at the Visual Studio code online on GitHub, and you can make suggestions and you can change it. So actually internally in Microsoft, the engineering teams are changing to be more open. So they're actually developing their code in the open. Whether this means Windows will eventually be open sourced, I don't know, but I know that other services like Visual Studio Code, and parts of Azure, services on Azure, are actually open source, and you can go look at the code, contribute to those things at the moment. So this is a real transformation that's real, it's happening in Microsoft. But of course, for you as a user, of course, you can use whatever you like. One of the things that makes it easier also to use is the marketplace. So a lot of customers and people actually bring their software and make it available to use. So if you don't want to do all that stuff yourself, set it up, go to the marketplace, look for something that you need, click a button and stand it up. We have a partner called Uber Cloud who basically use containers to take all of the scientific software and make it available. So if you search for ANSYS Fluent or Star CCM or one of these packages, OpenFOAM, you can get it in a single button and click, and then you have like an OpenFOAM or an ANSYS Fluent machine to use. So they make it that easy. So of course, if you are building applications, you can think about putting them on here as well for others to use. Maybe make a little bit of money out of things as well. In terms of us being hybrid, this is what we talk about, because some of the other clouds will tell you that you have to do everything in there, right? Or that's the way they think. And that's fine, but we know that not everybody is at that level. So hybrid for us means a true combination of what you have already perhaps on site and the interaction between them. So for people, a lot of companies have all of their identities, all your emails and everything in Active Directory. So this has been a core product for us, of course, over the years. We have an equivalent in Azure, and to be able to sync those identities and have one identity for an organization across the cloud is very important, and between organizations as well. We have something now called Azure Stack. So for example, if you want to actually have Azure in machines on your site, you can do that. So why would you do that? Okay, one of the reasons the people that use Azure Stack are cruise liners. So cruise ships, they're not always in internet connectivity the whole time. And they have a lot of services on the cruise ships. And developers for those companies write applications. And they only want to write them once and write them in one way. So if they can write them against Azure, then they know that when the cruise ships are not in connection to the internet, they still have Azure Stack. Everything is exactly the same. The APIs, everything is the same. So everything will work on Azure Stack the same way things will work on Azure. Not all of the features are available, and you have to buy things in a special way, but it's only a new product as well in the last year. But this is the type of scenario if something is disconnected right in one way. And of course then in terms of data and then security as well. So in terms of data platform, of course from SQL Server, which runs on Linux now, by the way. Nobody ever thought that would happen, but that's very interesting and performs very well with Red Hat Enterprise. But also then to security as well, which is, as already mentioned, interesting, important, and we always want to comply with whatever people have on premise. So policies that people have in place, security policies, they can be matched, and there's lots of tools for managing that in Azure as well. In terms of the intelligent aspect, so this is where we have these other services starting to come in. We have an Azure Machine Learning service. We have a bot service. So for example, with the bot service, you can just feed it a load of questions and answers. It's very good for customer service, and then automatically you will have a bot that will answer all of the questions. So this is as a service. So even, for example, if you were developing some code and maybe you have some users using the code and you have basic FAQ or Q&A, questions and answers, you can make this available as a bot. And you can go think about something else while your bot is answering all of the questions for you about your software. So that's one thing that you could potentially do. And then the cognitive services I mentioned, I'll come to these more. So I mentioned already maybe doing a translation. If I send some Spanish or translate it to English, but also into vision, speech, search, all of these are possible. These are all individual APIs you can use. So for example, send Azure an image and say, where are all the cats in the image? I want to see all the cats. I want to see no dogs. I want to see only hot dogs. Those sorts of things, you know, you can use with the Vision API, and of course with language as well. So I know with Cortana, which is the technology that our language is built into, a lot of the researchers in Microsoft Research have come very close to human language translation in Cortana. And finally then some of the IoT suite. So IoT, Internet of Things. Let's get away from also just the single cloud and get out to the world. What's happening in the devices that are we all have with us, the mobile phones, but sensors, things that are happening in buildings. There's so much data that is collected everywhere at the edge. And the Internet of Things is all of these things being connected with all of the data that will come back. What can we do with it? So if you were to collect all of those things, maybe process or analyze in the cloud, go back out to the sensors and the devices, there are many scenarios for that. And we're working heavily in that space to help enable people to do that. In terms of the trust, I mentioned earlier about security, and I'll play a little video now I think is coming up, but basically we have more compliance offerings than any other public cloud, and more than likely than any other service, physical, hardware, computing, data center. And I built data centers for 4 years, and basically I would never build a data center again after I went to the Azure data center. So the controls that are in place, first of all, for me to be able to go there, the physical controls that are in place at the site, the way the data centers are built in terms of the access, the way I can get access, all of these certifications, not just global certifications like ISO or SOC for financial regulations, but also down to particular governments. This is US, but we also have them here in Europe as well. GDPR is something as a regulation that's very important to us as well. Separate data centers, we have a lot going on in that space. But in particular industries, it's very important. The health industry, everything we've already done, we can only do because we've also been able to get certified, and the data centers have been able to get certified. And down, of course, into particular regions. So there are specific government regions that are owned and operated by the local government in the country, and they control the data, for example, in that region. They know nothing wants to leave. Only Spanish employees will work in this particular data center. So these are government data centers that we also have around for that extra level of trust. In terms of the span, we have more locations than anyone else. So we have gone for scale rather than sort of larger data centers in particular places. We have 42 regions. So these are locations around the world. They're actually maybe a lot more data centers. So maybe there's even up in Dublin, where I was, which is the North Europe region, has maybe about 20 data centers in a 1 kilometer, 2 kilometer area. So there are about 150 data centers in total. There are 42 regions. And this is already out of date. There should be 2 down here in South Africa as well. And you'll have heard that we built an undersea cable to Europe, also with Facebook, to get more connectivity between all of this. So between all these regions, also, it's connected by one of the world's largest networks. 1.6 million miles plus of fiber connectivity connects all of these data centers together. And not just our data centers, but partners' data centers. So people like Equinix, people who host data centers already, we have connections directly to those data centers. Yeah, please.
How come you have 20 data centers in Dublin?
So,
how do you define a data center?
so the next piece coming up is a video, and I'll show you. But very quickly, a data center is like basically like a big hall, okay, with a load of machines. That's basically what it is. And the thing is, when we built the first data center in Dublin, which was, I don't know how many years ago at this stage, the technology was different to what's available now. So I think the original data center in Dublin took maybe, did it take like a year to build? It has 3 floors. It has your sort of your aircon, your machines, your power on the bottom, machines, aircon. The designs of data centers are very different now. Originally, they thought, we'll make these big halls, we'll make them like a fridge. We'll keep all the computers cool. That was what they thought. And then they were like, well, actually, the manufacturers don't need to have the machines cool the whole time. So maybe we don't need to spend all this money on making it like a fridge. And maybe we could just actually run the machines hot, and they're still fine. So the design thinking has changed a lot in data centers. So for example, when I talk about 20 data centers, like that, maybe the first one took like a year to build, as all these things. Now they build them like car parks. So it's like, you know, flat piece of concrete, very thin outside. They can take the whole data center down and put it back up again within 3 months. So as the new machines come in, the new technologies come in, actually then it becomes cheaper to use the newer data centers. So the older data centers are older and the power usage is less efficient. And in the newer data centers, they've got newer machines, better designs, quicker to work, and actually it's more efficient and actually cheaper to use some of the computing in there. So the economics of the data centers, and we are also a service to ourselves. So Bing, for example, and different teams use Azure inside Microsoft. They're big customers of Azure inside Microsoft, and the economics of which data center they want to put their stuff in is also very important, you know. So they everybody wants to run cheaper.
Will you keep the old data centers functional?
Not all of the time. So some of them basically, as the old ones are, maybe as the old ones are less efficient or cannot be changed or cannot be upgraded, you know, obviously we want to do that. We want to upgrade them. So the data centers can be upgraded. So in terms of Dublin, I mean, I don't know any more specifically about if old ones will change or whatever, but I do know as the new technology is coming in, then it will make more sense to keep using the newer stuff, and eventually we'll have to refresh the old stuff. So I think maybe, okay, here's a little video if it works. I don't know if the sound will play. There's some very dramatic music playing here now, but It's just 1 minute. This is Dublin, actually. All of these machines, actually, the design as well is open source. So you can go onto the Open Compute project. Facebook also work with this. And the machines, the designs of the machines are completely open. So you can build your own Azure machine, if you like. The reason we do that is also that we can get more. So we can say to Dell, make us some, HP, make us some, IBM, whatever, make us some, you know, and we can get as many as possible as we need. Keep an eye on the time, actually. So. Okay. So you can see some of the designs have also changed from, some, well, okay. Some of these were chillers on the roof. There's a sort of a spine model going on now in some of them. So this is all real as well. So
how hot do data centers run today?
That's Singapore as well. I think it's Singapore. Well, actually, I don't know to both questions. So I don't know how hot they currently run some of them, and I actually don't know if it's possible to share. But yeah, we can find out. I'm sure.
It used to be sort of 14 degrees Celsius before.
Yes, yes. I think they don't run at that temperature anymore. So like that, maybe the cooling is done a little bit differently. And this is actually something as well that they get cool air cooling. So, and this is why they like Ireland and Norway and Iceland and stuff, because it's cold all of the time. And actually the cool air from the outside is enough to go through. And it's the old Egyptian technology from thousands and thousands of years ago, where if you wet a sheet and hang it over a window, the wind coming through the window, through the sheet, will, you know, send some cool water right into the air. This is actually very similar technology to what's currently used. So there's enough cooling coming from that to keep the machines at the temperature that they need. Okay. Okay, let me keep going, because I suppose I'm getting a bit too enthusiastic now. Really, I'm getting into it all. So some of the things from a HPC perspective that also are very important for us are the fact that we scale. So one of the most important things we have that a lot of others don't is Infiniband. Infiniband networking, not just regular Ethernet networking. We have low latency, high bandwidth networking with Infiniband. So we have the latest QDR, FDR, EDR technology available. So if you want to create a cluster, this is what makes it very real. We have many different flavors of compute instances I can go through that you can choose. You don't have to use one. You can use a small one. You can use a big one. You can use with memory. You can use with GPU. All different flavors that you might need that you can combine to use for your calculations. And then like that, some of the special technologies that people may not always want to invest in themselves on site. Maybe you can get a GPU and do some GPU calculations in your workstation, but also GPUs are very expensive and they go out of date very quickly. So as the new ones are coming in, we at the scale that we have are able to get the latest ones that are available. So we have the P100s, we have the V100s, and we have K80s and whatever else. We have a lot of these cards available that you can use for different types of scenarios. More than Infiniband, we have the special networking, FPGAs, field programmable gateways, where you can program the chips to do what you want. And at that particular level, you can get a flexibility, but you can also get performance. And we use that to get very fast networking between things. Okay, let's keep going. This is a little bit of a detailed idea, but these are the typical scenarios that all people using the cloud for HPC are generally doing today. Okay, so we have this kind of cloud bursting idea, which I talked about before. So maybe you have a machine on premise and you have a cluster, and then maybe you want to burst some calculations to the cloud every so often. So this is using the same software, the same scheduler. Maybe you like to use Univa Grid Engine, Altair, PBS, SGE, whatever. The same software can control what you will use in the cloud. The other way to think is that you will have an individual cluster for each person. So make your own cluster, do your simulation, shut it down. This is what we have, the cluster on the cloud type of idea. Our cloud cycle computing colleagues help this to happen. And then also people use remote workstations. So maybe they have when I worked in an oil company, we had €16,000 workstation. We had two 30-inch monitors, and we had people doing interpretations on three-dimensional graphics. They needed GPUs to do this. So you think, okay, we can't really do this in the cloud, but we can. So with special software, where even it's not just remote desktop, it optimizes the pixels that are transferred from your desktop to the cloud. And actually, you can get an interactivity with a model that makes it very easy to use. Maybe you can use it on an iPad, you can use it at home. So people are using remote workstations in the cloud. And finally, you don't want to worry about all the infrastructure stuff I talked about. You just want to write code, you want it to scale, you want it to shrink. We have a service to do that. It's called.
Sorry for this one. Then you can use this post-process script to generate the peer review files. And if you have done that, then using the same method how you moved files to Magnesium, move the whole TMD folder back, this TMD folder back to your notebook, where usually, hopefully you already have peer review. And I will come back to this slide for those who need it. And in peer review, in the file menu, you can use open file, and if you navigate into this TMD folder that you just created with the simulation, then you will see red blood cell, platelet, and fluid fields. Now, I would suggest to first select the red blood cell files and use the XDMF reader. Peer review will pop up an option what reader you want to read in the simulation data, and from that, use the XDMF1, not the XDMF3, because that has some compatibility issues currently. And this XDMF reader will just read in whatever file type you select from this folder file, like red blood cells, platelets, fluid. If you read in red blood cells, then on the left side of the properties panel, you have to press apply. This is because peer review is prepared for very large data sets. It's typically a tool for HPC application output visualization. And unless you apply some command, it will never start to do it, because you might load in a 3 terabyte data set. And if you accidentally press something you don't want when it starts a computation for the next 3 weeks, that might not be good. So it will always ask for some confirmation, whatever you do. But after you press apply, then it will automatically read in red blood cells. And you can give different colors on the toolbar for it. For example, in this sample, I colored it by the force exerted on the cell. And you can see that, and you will see on your version, that the two ends of the cell is colored differently, meaning that we are forcing it here and here. If you remember, this is the place of the two silica bits, how we stretch our cell. And since you've saved multiple times from the simulations, you can use this gray button and the rest of the buttons to step back and forth in time. So you can animate your simulation how the cell is being stretched. And of course, you can apply all kinds of filter. You can cut it, slice it, color it by different forces, check out how the viscous forces work. You can also read in the fluid field if you want. That's again going to the open menu, navigate, blah, blah, and open the fluid files. Then in the same window, you will have a fluid background as well, on which you can add, for example, arrows for velocity. You can check the velocity around this cell while you are stretching it, how it evolves. You can also check for platelet files in simulation where you actually have platelets. Here it's just a single red blood cell. So you will have red blood cell. If you can, then please do check out how it looks in peer review. And for the rest of you, I try to help you to get here. This is just an introductory application for Mimocell. I really would like to move on so that we can create an actual blood flow in a vessel, not just a single red blood cell. That would be a bit more interesting. All right. So again, who still needs help? I try to run around for a few minutes, and then we'll continue. All right. So again, who still needs help? I try to run around for a few minutes, and then we'll continue. All right. So again, who still needs help? I try to run around for a few minutes, and then we'll continue. All right. So still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So again, who still needs help, I try try to run around for a few minutes, and then we'll continue. Alright, so again, who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so again, who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes, then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, so who still needs help, I try to run around for a few minutes and then we'll continue. Alright, So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for a few minutes and then we'll continue. Alright? So and who still needs help, I try to run around for.
And you get the full software stack with when modular ready. Okay, so we saw the batch scheduler, we saw the software stack, so more or less you and bash scripting, so you should have more or less everything to be able to run on a HPC system. Before actually running, is good to understand also which file system are there and how to use that. So every system has its own different configuration. This is Mare Nostrum is, for example, has three main partitions, let's call it. One is the root file system that you don't access, is where the OS is stored and the application is stored. Then there is a GPFS, it's an EPM file system that is distributed, efficient I/O, and it's suitable for a supercomputer. And this is where all the main files, your OMAR, all the files you put into the machine, gonna be, etc., etc. And then, as I told you already, there are these local hard drives on the compute node. As I told you, the main file system is this GPFS that is actually divided in different parts. You have the apps folder that contains all the application, and then this is there. You can list the applications that are listed to get an idea, but you should not have access to that folder. And then you have home, project, and scratch file system. These are different, are all on the same GPFS system, but are for different purpose. So home, I already told you about home, is where you log in, where you have your file when you log in immediately. Project is a specific folder designed in Mare Nostrum to host file that you can share with other people. So project has a group folder, so you have your user, as I told you before, is part of a Unix group. When you have an account in Mare Nostrum, you get also your group, get a folder in this project file system. And you can put there files that you want to share with other people, because other people in your Unix group have access to this folder. And it's a way to share file or to have like same software working on the same file and like that. It's intended to store data that needs to be shared. And then there is Scratch. Scratch is useful for you when you run your simulation. It's a file system that is distributed over all system. You can see it from the login node, from the compute node, and is where you should put the temporary file that your code is generating, okay? And it's not backup, and it's usually cleaned regularly, so it's not meant for long-term storage. It's only for temporary files. It's maybe you have your code that needs a lot of parallel I/O, or really, so that is the folder. Okay. Again, there are several inputs, several examples that I prepared already.
It freezes completely all the time.
Okay. I think there are like, I don't know if it's this connection, because maybe the connection here is not excellent and it drops and then it freezes. This, for example, you saw I left this open and it's still there. Okay, so yeah, I think that the login will stay for the rest of the training even more. I don't know how long it is. So if you want to play with this, you can keep playing. It's not only for today.
3 days.
3 days. Okay. Okay. Again, I have other. Okay, this is a more sophisticated submission script, as I told you before, and these make use of one software that is installed, Python. You make use of the Scratch, dir, and it does a lot of other small things that you should get. So let's go quickly through this. Again, don't focus too much on the single command. If you have a question, ask me, but all of these, if you Google it or if you type command on the command, you will get many more information than I can give you. So don't forget, let's try to understand the structure again and what you do and what are the things you need to do. So again, definition of which resources you need. In this case is a sequential, so only need one processor. You load the tool you need, in this case Python. You set up your, I set up my Scratch. So this is the path I was telling you before. GPFS, Scratch, the name of my group. This is a variable in Bash. It's called, there are built-in variables, so Bash, the shell itself sets some variable that you can use or that are used to influence the behavior of the Bash. This user is a variable, and with $ in front you get the value of the variable. That is your username. So basically here I set up a folder like this. Slurm job ID is another variable set by Slurm this time that contains the job ID of the job. And That's all. Submit, this is the current directory, and then what I do, I create my folder, because this is present already, but this needs to be created, because I want a specific folder in my Scratch. So I create a folder in Scratch, I copy my executable, I have an executable pairwise that calculate, you give an array with n particles, for each particles the position x, y, z. This Python script calculate, give you back a matrix m by m with all the distances, reciprocal distances between the point, the pair distances. It's a really trivial code that does some calculation. So I copy my executable into Scratch and I move into Scratch. So I CD into Scratch in a way that everything that I produce, every file I produce, they will be already in the Scratch. Freeze. Okay, that's the.
I've already sent 2 emails to the help desk.
Oh, thank you. Yeah, thank you. But again, okay. So 1 second, I'm trying to get the same script from my local computer, so that I can show you. Okay, this is the same. We were not able to run it, but it's okay. So again, we were here. Again, give executable x permission to the executable, and then here I did a small trick to trying to time how much it takes this application to run when I run it, how much really this code it takes. So it's really easy. There is a variable, built-in variable in bash again called seconds. Seconds, when you start the bash, it starts accumulating second integer in this variable until the bash is over. Okay, so at any point you can ask the value of this second to get from how long this variable was started, the bash. What I did is a small trick. Before executing the command, I set this variable to 0, so I reset the second, and this does, the bash still accumulate on that, but it starts from 0 instead of the time when I started the script. It's a very bad way to calculate time, because it gives you like, it's not exact, it doesn't give a, but it's to show you that you can do something like that. So you get to 0, at the end of, after the execution, you get the value and record it to time, copy back results to your final folder and print some other running time, the print the time it runs, and equal, and say ciao. Okay. Let me, I have a good thing. I wanted another thing I wanted to show you. Okay, wait a second now. Yeah. Okay, so that was a serial job, okay? That was not parallel, it was a serial running on a single CPU for the time taken. And that is, it can be, that is, okay, this is a really basic introduction to how what parallel computing versus serial computing means, to let you understand better what means when you run on multiple nodes or when you run on a full node, not a serial program. But I'm not going into details of any library or technique used to parallelize. Again, you're going to have this afternoon, I think, a section on parallel programming and algorithms, so much more information. But simply to tell you, if you have a problem, you can divide your problem in several sets of instructions. If you execute one instruction after the other, This is serial computing. And that was the bash script, that is what it does. In the script I show you, you have a command, after that another command, after that another command. Imagine I want to perform the piecewise code, run it for 10 input files, okay? If you do in a serial way, sequential way, you have to wait the first, that finish, then start the second, etc., etc., etc. One thing to do is to use the parallel nature of the node of this machine to distribute this problem. So again, you have a single problem, you divide it in instructions, each instruction is independent from the other, so why not one CPU start the first instruction, and in the meantime you can use other CPUs to start the other instructions, okay? So that's, these ideally will speed up your calculation proportionally to the number of CPU that you can use. Okay, let's see a really, again, basic example in okay, so again, this is, okay, again, I prepared for your submission script. You can run all this file, you can run directly straight up from the material that I gave you. So if you have if you want to try, modify, please go. Because this is the same as before, same input file. The only thing I changed, it was dim here, before it was 500, I think, is the input file. And there was only one value of input file, so I was performing that pairwise on a vector of particle that was only 500 particles, okay? And I wanted that calculation, that's all. In this case, I want to do 1 over 1,000, another calculation for 2,000, another calculation for 3,000, 4,000, 5,000. So, and you see, the problem gets even bigger. So, if I do sequentially, I will wait all day. I didn't change anything else. But we can tell the bash to do that in a parallel distributed way, task-filing way. And the same as I was showing you the picture before. So if you have like, if you have a 5 input file, why not have 5 CPU working at the same time of that input file to produce some data? And how do you do it, this in Bash? Bash has a really nice functionality, that is that you can put process to the background. What does it mean? When you were typing a command, any command, you were basically on the command line, you were waiting for that command to be executed, to finish, in order to get the prompt, the line again, and able to run another command. If you, after a command like this one, this is calling pairwise for an input and redirect the output. If to a command you put an ampersand at the end, after the command, you will see that no matter how long it takes for the command to run, you will have the prompt immediately back. That doesn't mean that the command has already finished or that it's killed, or the command is running in the background, okay? And you can background as many processes you want. That was clear? Did you understand? That's the same as the picture I show you. Distribute over the number of CPU. So you have a 5 CPU, you need 5 computation. You start your bash scripting and you start the first computation and you put in background. And then you get another, you get back the command line immediately. The computation in the background is running, is producing data, is doing whatever you ask it to do. You get another command line, you can run another command and with the ampersand and it goes in the background again. And you can do this. And all this job will be distributed over the number of CPU that you have. Be careful that if you do this 100 times and you have only 5 CPU, you will have processes, 2 processes running on the same CPU, so slowing down each other. So needs a little bit of orchestration, needs a little bit of thinking, but this is a really effective way to run on a supercomputer. No communication, no interchange of data, every task is independent from the other. And here I did all these things that seem so complicated in these 4 lines. That all the rest of the script is the same, except that I have a 4 input instead of 1. And I use another construct of bash. Bash has a lot of construct, if, for loop, etc., etc. I didn't go into this because it would take a day only of bash. But this is a for loop, and it basically loops for every input number that I put in that dim variable, so it was 1000, 2000, 2000, 4000, 5000, in loop. And so for I in, it's really semantic, so for every I in the list of value, do give the value, the first value to pairwise, redirect to this output, and put in the back. When you put the process in the background, what happened? That it goes immediately to the second line. Again, the process is not killed, it's running in the background. And it goes in the second line, this done, go back to the for loop and get the second value that is submitted again and put it in the background. And do this for 4 times, for all the input you gave. What's happened? But if everything is in the background, the code is going to be here, is going on. The loop is over, it is going to go on. But you have still process running, okay? So you have to put this wait here, that it waits that all the process in the background are done before getting the next instruction. Why you need this? Because again, you are behind this batch scheduler. You have an allocated node. So if you reach the end of your script, the scheduler will think that your job is over. It doesn't check if there are processes in the background running. There are many processes in the back all the time running it. So if you don't put the wait, this will spawn 5, 4, I don't remember how many, processes running in the background. But when this is going through, it goes, it will tell you that there is no output, and finish, and you will be over with this process still running. So this is very important. You have to wait until the job is done.
Why don't you use time for instead of seconds?
Yeah, because time is actually the best tool you can use. And on the serial one, I could have used time. So if you run these 2 examples, the serial and the parallel one, it will show you that if you use the largest input file that you use for both, is going to be the total time, because you don't have sequentials, okay? If I will do that with time, I can put time in front of a command, okay, here. Then I will get the time of only that command, not of the full 5 process running. With this second, it's much less accurate. I don't, it's not a good way, but you get the actual whole time that passed from here to here, not the time that this executed, okay? I don't know if I was clear, because that was to show that basically running 5 processes in the background in parallel, it will take, the full calculation will take as the longest one, okay? Because all the other will finish before and the longest one. They start all at the same time, the fastest finish, the long one takes 1 minute to run the 5000. After 1 minute, you are over. And that's the same duration as a sequential, with only 1 input for 5000. But in this case, I ran 5. Okay? That's really something.
Is there a way with a simple script such as this one to actually pick your processor?
Good question. So usually this is something like that the OS manage, like thread affinity.
Scheduler or the hypervisor.
Yeah, or yes, okay. Then for sure there is. I'm pretty sure there is.
With Bash? You could do this with Bash.
Good question. I'm not sure. I should probably Bash. It's not. No, I don't think Bash has. Then maybe I'm not sure. I can check. But okay. So okay, that's. I show you the parallel, the ampersand and wait. Okay, and that is a kind of parallelism, that is a way of parallelizing your application. And this one, task parallel. So you have many independent runs. It needs orchestration. So in my case, orchestration was the for loop and the wait. There are much more sophisticated tools to do this type of orchestration, because in my case it was also easy. I had 5 input file, 5 processors. Okay, so I distribute one each. What if you have 100 input file and only 5 processors? Okay, you say easy. I do a round robin. Yeah, but you don't know which one. If you don't know which one is going to end it first, you may end up with unbalanced load. That means that imagine one CPU get all the fastest run, okay, and one CPU get the extreme case, and one CPU get all the slowest. The first one, it will wait idle, doing nothing forever. There are tools to manage load balance and distribute. So first finish, the first process to finish, get another one. There is a tool in Unix, very powerful, that is called Parallel. It's a new, that does this in automatically really beautiful way. You say parallel J4 and an input file and a list of parameters, and it automatically assign one parameter to each of the process that is running, and the first who finish get the second one. On Cartesius we have another in-house software called Stopos that does this also intranode. There are many tools, but the important thing is that you need an orchestration.
If you have the details that you use to make it, delete it and create a new one which has the GPU that you need. Yeah. So for example, in this particular area, you can see I've got my machines, an IP address, some storage, networking. I can click in and get more information about them. So if I click into this machine in particular, it should show me some information. It gives me the name, where it's running, the subscription, an ID, my public IP address, the type, if it's Linux, and I can get a little bit of statistics about it for the last, one time, CPU, network. And then there's all of these things down here that I can do with the machine as well. So for example, if also I made this machine by hand and then afterwards I wanted to get code from it, if I go down and click on Automation Script, what it will do is it will show me the whole machine and the configuration as code. So this is in JSON code at the moment. And maybe if I don't like it in the, so Azure has its own templating language. It's JSON formatted. It's called ARM, Azure Resource Manager. So it's basically JSON description of the machines. You can see the details there. But actually, if I don't like it so much in that format, and I want it in the CLI, then it will show me in the CLI. Or maybe I want it available in PowerShell. So show me how to make that machine in PowerShell. There are all the PowerShell commands to make that exact machine. If I want it in .NET, this is the .NET code that I will use to create the machine. So this is a very powerful way, because maybe you go in and you tinker in the portal with what you want first of all, and then when you're happy with it, stick a pin in it, you're done. Get my code, take it, delete everything, and then I have my code that I can recreate the whole thing with. And even for reproducible research, if you guys are making papers, doing simulations, and you've the machines that you use to make the simulation, if you keep the configuration for this, at least the whole thing can be repeatable and can be shared with somebody else a lot easily. So this is the infrastructure as code type of thinking that you can have. So of course then you can all do different things with the machine, so you can set different backup and recovery options as well. So okay, we won't go into some of these maybe now. Different metrics and things like that you can have. So this is just kind of a little bit of a picture of what maybe Azure looks like. And then on the command line, maybe you can interact in a different way. So let me see. I know we're coming to the end. So is there anything else in particular that I'd like to show you or like to discuss? Okay, I might show you the cycle computing thing now just in a second, because so basically when we talk about, and this, I'll make available these slides and the labs online if you want to choose it, but from moving from Azure IaaS to sort of HPC IaaS, so if you're basically making HPC infrastructure as a service, or you want to use the HPC PaaS service or Azure Batch service, Or if you want to use HPC software as a service, more like the Uber Cloud thing I just showed you, these are the different things that you could do. In HPC IaaS is where we have a lot of interest. People like to still have this control. They like to make their own clusters, their own machines. This is where we have maybe 2 different options, 2 different tools that are available. So one which I'll show you now, I'll do a little demo, is this Cycle Cloud tool. So this is maybe where you, either as an IT organization, you can own it and give this panel to your users, or maybe you as a user have this to run and deploy your clusters. This is free, completely free, right? So what you'll do in Azure is you'll pay for what you consume, the compute, the storage, the networking. That's what you'll pay for. But a lot of the other services, some of them you'll pay for as well. In HPC, Cycle Cloud is free, Azure Batch is free, the Microsoft HPC pack is free. So when you're using those tools, you'll basically get them for free. So there's a lot of really great capability available for free, and you're just consuming what you need. So I'll show you a demo of this in a second. The other one to mention is traditionally Microsoft had a Windows product called HPC Pack. A lot of financial institutions still do this. So it basically is a queue management software and a resource management software. So if you have a bunch of Windows machines or Linux machines controlled by a Windows machine, you can have queues, you can have a nice little GUI to submit jobs. So because this also is free, a lot of financial institutions pay a lot of money to IBM for their scheduling software, so they don't need to do this. Maybe it isn't quite as advanced as that, but this is still working, free, schedulable software that can schedule jobs, run jobs, and so a lot of companies like to use that in particular, particularly if they're very Windows-centric. Okay, let me jump into a little bit then about, okay, let me show you Cycle. What it's like to create it. Okay, so this is actually something you can run on your laptop, if you like. So at the moment I have this running on a machine in my Azure subscription, and I'm just going to it on a public IP address, a public DNS name, and basically I've logged in and I have this kind of little panel available to me. On the left-hand side, I have the clusters that I can see. At the moment, I'm in a cluster called HPC Lab. I can see that that's when I terminated, everything's off. I can start it, I can change it, I can do all of these sorts of things. Down here, I can make new clusters and I can delete clusters. So what we'll do right now is we'll just make a cluster. We'll just make a system. So let me click on the plus button. This is the default templates that it comes with, not very much. We have a whole bunch that we should make available to people. So even if you want a MATLAB or you want something else, you can click a button and get something available for free. So in this case, I want a grid engine cluster. So I'm going to click on that. It's going to give me it's going to give me 4 things to go through. So maybe I'll make a Barcelona. This also works with other cloud providers. So while we purchased the company last year and we make it available with Azure, it is also working with AWS, with Google. And these guys have been running 10 years. They've done a lot of big work for companies to make things work in the cloud. So what am I going to log in with? I'm going to log into my internal subscription. And where do I want to create the cluster? Well, I'll go home. I want to create it in North Europe, which is actually the Dublin data centers. So I'll click on next. What software would I like? Okay, so I'm okay to use CentOS. You can choose different types of software that they might have available. If it's not there, we can put it in. These guys use Chef. If you've ever heard of Chef, it's a sort of a scripting language for doing sort of automation and things like that, and for software installation. Very powerful. These guys use Chef under the hood. You can make your own Chef recipes, include that in here, and you can set up things and configure them in that way. Yeah, so if you prefer to use Ansible or another automation tool, particularly on Linux, but also on Windows, you can use those tools too. This tool has Chef baked into it, so if you know Chef very well, and like this tool is changing all the time. Since they joined us as well, there's a lot of things, integrations they're doing with Azure in particular.
Just a matter of religion, Chef, Puppet, Serve.
It totally can be, and that's the other thing too. If you, whatever you prefer to use, you know, I think don't change it, right? So I mean, you could still stand up for it. You can use, I love Ansible in particular, and I just Ansible modules for doing things with Azure. So you can write a playbook and stand up things in Azure, and then you can use Ansible modules to install things on top. So you could totally run that way if you prefer. So people find this tool very easy to use because only in a couple of clicks you can create a cluster. So for example, if I want my master to be a particular type, And I want my execute nodes to be another type. So in this case, I'll just use the standard A4, which is the cheapest. So let's do that just for our demo. They have 8 cores. So this is where as well you can start and stop automatically the nodes. So by default, if I leave that ticked, it will create me a master node, won't make any execution nodes. And then when I submit a job, it'll stand up a bunch of execution nodes, do my job, shut them down. So let me try and demo that. And maybe I'll say the maximum amount of cores I want to make is, I don't know, 64 cores. So I put a limit on it. I say that I want to report back their state. I say that I want to use a computer network I've already set up, and I save it. And that's it. It's as simple as that. So I have a new cluster called Barcelona. Everything is off at the moment. I have a master template, 1 node. Nothing's there. I've just created it. So let's start it up. Okay, are you sure you want to start? Yes, I am. And off it goes.
You have no job there.
Sorry?
You have no job there. So
I've no job, so actually the cluster was off. So I just created it, but there was nothing created. It just sort of made a configuration and didn't do anything. So when I pressed start, it's actually creating these machines from scratch. That's actually what's happening now. So I told it I want a cluster no more than 64 cores. I want to use the A8 instance, and I want it to be in North Europe. And after that, it's like, okay, well, I know that, thanks. And then when I press start, it will create that for me. So what's happening right now is you can see it's creating the master node of the cluster. So maybe if I click on that, I might get a bit more detail. Okay, shows me it's acquiring. I think it already has an IP address. So this might take a few minutes to do. So we can talk about a few other things while it's doing it.
why does it take so long?
So actually the way this tool is working is it's validating, because it's creating everything from scratch, it's validating a whole bunch of things. So like where can it get the number of machines I want to the particular area with the configuration. There's a lot of checking that this thing's doing under the hood. So this is actually slower than doing things in Azure. So raw. So for example, to create a cluster, it might take maybe 7 or 10 minutes here to make the machine, submit a job. But say, for example, with the Azure CLI commands, I can make a machine, I can make a virtual machine scale set, I can do those commands myself, and it's pretty quick to do that. So for example, I was with a customer 3 weeks ago and in the US, and we made a cluster of 20 nodes, 480 cores in total, 4 terabytes of RAM across the whole cluster, and with 2 commands, we made that cluster in 7.5 minutes. So the cluster was available with all those cores, those nodes, in 7.5 minutes. We logged in, ran a simulation for 2 hours, and then that was basically what we did for them for testing. That whole process cost $160 US. So they ran that simulation for 2 hours, took 7.5 minutes to create the cluster, log in, and the whole process was like, basically $160. So that was a pretty powerful thing to be able to show them. So I did that separately with Azure CLI commands. But the thing is, if you're not so comfortable with commands and you prefer something nice point and clicky, a lot of people prefer to do this. And this is something that can be shared with people. You have a template. So also this is being worked on all the time. So these guys joined our team middle of last year. So we only started to meet them then last year. They have a product team that's integrating with Microsoft. They're integrating this with Azure. So the tool will improve also, I think, in terms of the speed. But the powerful thing about this is often that, when it is all started up and it's created, it'll only give me a master, no execution nodes. And then when I submit a job to it, I can submit as many jobs as I like, and it's only going to then run the execution nodes for what it needs.
So creating slates will take so long?
Well, we can see now. So it should probably take, well, actually, I know we're running out of time. It should take a few minutes to do. Let's see if we can get it done. So it's starting to come online there. You can see this.
It says uptime 70 milliseconds.
Okay. And the whole cluster up 3 minutes, 20 seconds is when we started it. So 0.8 core hours, you can see. The other thing you can do is sort of create alerts. So for example, if you had a particular budget per month, say you wanted to do $100 per month, for example, you wanted to email somebody, a particular recipient, for example, It's my email address. And save that, and then I have a little notification, so if I'm going over my budget or something, the user can do that. So, okay, maybe do I have one that I should have one I've already made or started, but actually I think the rest of them I have turned off already. So you can see the ones that are started that are in bold. Just while we're waiting for it actually to start, then there's a few of the other panels you can look at, so you can get statistics, information on what's happening in the cluster. Jobs that have been submitted, there's nothing there at the moment. Is there anything interesting to look at? Gangly is a tool that can show all of the clusters that's available. Computes, okay, there's nothing running at the moment. I should have had something ready, sorry, to show you, but actually, sort of while we're talking, I know we're get to the end of time. It's almost 1 o'clock. So I'm sorry that maybe I gave a presentation and we didn't get stuck into some of the things. I will make sure that you have the slides, the presentations, the link to our GitHub, so that if you want to do specific labs, you can. And my contact details, so really I know I haven't had a chance to actually meet all of you and hear about your research and what you're doing, because I'm always interested in that sort of thing. But please, if you want to reach out directly to me afterwards, anytime, just go for it, right? Mail me, find me on Twitter, whatever. Send me a LinkedIn request. If you want me to help you with something, I'll do my best to do that, or put you in touch with colleagues who can help. So that thing is still going. So when it says ready, then I mean we should be able to submit a job. And what I'll do is maybe I'll make a little video. I can send it on of it happening as well. And is there, so Dwayne, is there, okay, so I suppose as well, I've just given you a bit of idea of maybe what it's like to use the cloud for HPC, what other people are actually using the cloud for HPC for. There's lots of things further to get into. This is like the tip of the iceberg, right? We can talk about costs, we can talk about, like that, more details about things you're interested in, maybe in security or infrastructure or development tools or whatever. But I mean, really, the main thing we want to try and get across to everybody is the power that we have for anybody, any one person, to create this kind of compute capacity that anybody can do this in the public, right? Can go online and get this. And power science, right? Power simulations, power things that you need to do, and have it be real. So please also as well, this is the first time we've kind of run I cut down a day's workshop to just 2 hours, and really probably I'm sure we could have done it better, giving you a little bit of access, seeing something yourself. If you have any suggestions for me, it'd be really great to hear them. So you can contact me separately, you can say it to me. I have to leave shortly after this, so I'm not able to stay around too long as well. But it was really, thank you very much for your attention for the last 2 hours. I hope maybe I gave you a few ideas or things to think about, and I really hope that you have a great workshop the rest of the day today and tomorrow as well. Okay, so thank you. Cheers.